They're all welcome to this new session of the seminar. Today we have the pleasure of having Professor Novaes, who will talk about sliding Shilnikov dynamics in non-smooth systems and applications. Please.
Okay, so first of all, I would like to thank the organizer, especially Jordi Canela and Jonathan Regrossa, for the opportunity of giving a talk in such a great series of web seminars. Thank you very much. In this talk, I'm going to discuss the dynamics of sliding Shilnikov orbits, which is an object that have been introduced by Marco Antonio Teixeira and myself in my PhD thesis. Also, I will show an application of some of our results regarding sliding Shilnikov orbits in a non-smooth biological model. First, for the sake of contextualization, let me introduce the concept of Shilnikov orbits in the smooth context. We start with a three-dimensional vector field which has a hyperbolic saddle focus. P is the hyperbolic saddle focus. In this case, the eigenvalues of the Jacobian of the vector fields evaluated at the singularity has three distinct eigenvalues. One of them is a real one, and the other two are complex conjugated eigenvalues with real part distinct from zero and with sign with distinct sign of the real eigenvalue. This is the local description of the vector field in a neighborhood of the equilibrium. So a Shilnikov orbit is a closed curve composed by orbits, okay, which lives in the intersection between the stable manifold. In this situation, we have a two-dimensional unstable manifold and a one-dimensional stable manifold. So the Shilnikov orbit lives in the intersection between the stable manifold with the unstable manifold. So this is a homoclinic connection, which looks like this picture. Okay, to study the properties of this connection and also the perturbations of this connection, we need to introduce the so-called saddle quantity, which is denoted by sigma and given as the sum of lambda 0 plus the real part of the complex conjugate and the eigenvalues. We say in the situation that the Shilnikov condition holds when the complex conjugate eigenvalues lies in this band delimited by the modulus of the real eigenvalue. This means that the closest eigenvalues to the imaginary axis are the complex conjugated one. Okay, so if the real eigenvalue is negative, the Shilnikov condition is equivalent to say that sigma is negative, and if the real eigenvalue is positive, the Shilnikov condition is equivalent to say that sigma is positive. So we have the classical Shilnikov results. If the Shilnikov conditions hold, the Shilnikov condition holds, then for every neighborhood of the Shilnikov orbit, there exists a neighborhood of the vector field x such that each y in this neighborhood has countably infinitely many periodic solutions in A. So given a Shilnikov connection for which the Shilnikov condition holds, in a neighborhood of the Shilnikov connections, you can find infinitely many periodic solutions. Okay, and otherwise, if the Shilnikov condition does not hold, you can find a neighborhood of the Shilnikov connection which isolates the Shilnikov connection from the periodic orbits. That means that in this neighborhood, inside the neighborhood, one cannot find periodic solutions. Okay. In addition, we can find a neighborhood U of the vector field such that each vector field in this neighborhood possesses at most one periodic orbit. Actually, the Shilnikov connection is a codimension 1 object. So you can find an one parameter family of smooth systems such that for me, for instance, z x mu, such that for mu equals 0, you have the x, the original vector field, and for mu distinct from 0, you do not have the slide Shilnikov connection. Then for the Shilnikov connection. Then for mu, for instance, for mu positive, you have vector fields with exactly one periodic orbit, and for mu negative, the vector field does not have periodic orbits. So those are the classical results regarding Shilnikov homoclinic orbits, and our main objective here is to extend those results for in the non-smooth context. So we have to define what we understand for a slide Shilnikov orbits, and also how these features here appears in the non-smooth context. So the proof of these results is performed by taking a bidimensional transversal section to the Shilnikov connection, and to study periodic solutions. What we want to do here is to study fixed point of a first return map defined in this section. One can see that studying fixed points of this map can be reduced to studying fixed point of a one-dimensional map. And studying this one-dimensional map, we see that it oscillates infinitely many times towards the origin. And the Shilnikov condition, actually the saddle quantity, this saddle quantity controls the amplitude of this oscillation. So for lambda, for sigma negative, you have sufficient amplitude in order to this graph intersectly the identity infinitely many times. And in this situation, for lambda positive, for lambda 0 negative. If sigma is positive, then the graph does not intersect the identity. So you do not have a fixed point, and you do not have periodic orbits. Okay, so the idea here is to extend this result and concepts in the non-smooth context. So let me introduce the type of vector fields we are going to consider in this talk. So here H is a differentiable function for which 0 is a regular value. This means that the inverse image of 0 by H is a regular surface. Then we denote by omega r the space of piecewise smooth vector fields defined like this. So Zx is x if H is positive, and y if H is negative, where each vector field x and y are smooth vector fields. So if this set of smooth vector fields is endowed with the CR topology, we can see the omega r as a Banach space endowed with the product topology. Okay, so this is the space of vector fields we are going to consider. Okay, this is a piecewise smooth vector fields, but I have to establish what does a trajectory means here. What is the definition of trajectory? Because I have a vector field, I want to study their trajectories. Okay, so for points where H, for initial conditions where H is positive or negative, it's simple. I just have to take the local trajectory defined by X or Y, depending if H is positive or negative. But what happens if H is 0? If I take an initial condition in the discontinuity surface. Okay, so this is overcome by the Filippov conventions, where Filippov, what he did was, instead of consider a differential equation to define the trajectories of a piecewise vector field, you consider a differential inclusion. Okay, so given a system, a piecewise smooth system like that, they define what is called in difference inclusions book by Filipov's regularization. They consider this set-valued map, where for points where h is positive, it's just x. For points where h is negative, it's just y. And when h of x is 0, then you take the convex combination between x and y. Okay, so this is defined using this sign function, this multi-valued sign function. Okay, so Filipov states that a solution of the piecewise, this piecewise differential equation is defined as a solution of the differential inclusion. Okay, and the solution of the differential inclusion is an absolutely continuous function phi, satisfying that the derivative of phi belongs to this set almost everywhere. Since phi is an absolutely continuous function, it is differentiable almost everywhere. Okay, this is done in this book. And when we have a piecewise smooth system plus the Filipov conventions, we call this system by Filipov system. Okay, so this is a nice geometric interpretation of the Filipov's trajectories. Okay, we do not have to compute, actually to compute solutions of differential inclusions. Then to understand the trajectories of a Filipov system, we divided the discontinued surfacing in some regions. Okay, the first one is the crossing region, which consisted by points where one of the vector fields points inwards to the discontinued surface and the other ones points outwards to the discontinued surface. In this situation, the solutions in both sides of the discontinued surface can be continuously concatenated. Okay, so for instance, here is this vector. We have a trajectory, we have a trajectory here that can be concatenated with a trajectory on the other side. Okay. Of course, this cannot be always done. For instance, for points behaving like this. So in this case, both vector fields x and y points inwards the discontinued surface. In this other case, both vector fields points outwards to the discontinued surface. So in this situation, we have defined on the discontinued surface a vector field, which is called a sliding vector field. So if we took an initial condition here, the trajectory of this initial condition reaches the discontinued surface in a finite time, and after that it starts to follow the trajectory of the sliding vector field. So we can continuously concatenate the solutions at this point. Here one can see that we do not have uniqueness in the past, because if you take another point, it reaches the discontinued surface and eventually cross another solution. Okay, so this is a situation which happens in Filipov's system where you do not have uniqueness. Here, you have uniqueness in the future, but you do not have uniqueness in the past. This is a similar situation, but we call this escaping regions, where you have uniqueness in the past, but you do not have uniqueness in the future. So if we start with a point here, you can follow the sliding vector field and eventually leaves the discontinued surface whenever you want. Okay, so you do not have uniqueness in the future. Given an initial condition, you can have multiple futures. Okay, this region is called escape region, and this region is called sliding region. Okay, so there are other points in the discontinuity surface that must be distinguished. The first one, which will be very important for us, is the pseudo-equilibrium. The pseudo-equilibrium is just a singularity of the sliding vector field. The sliding vector field is a smooth vector field defined in a manifold. it can have singularities. So a singularity of the sliding vector field is a pseudo equilibrium for the Filipov system. So for instance, you have the discontinuity line here. You have your vectors outside its continuity. We are in a sliding region. We have defined the sliding vector field, and eventually you have a singularity of the sliding vector field. The main difference between this type of singularities and the ordinary ones is, despite it's a singularity of a vector field, for the Filipov system you have a direction where you reach the singularity in a finite time. So since it's in a sliding region, you have trajectories reaching the pseudo-equilibrium in a finite time. It will be very important for us. Another kind of points are the tangent points, which are just contacts between the vector fields and the switching surface. For instance, let's draw. You could have a contact of this type. It's a contact between one of the vector fields. Okay, so here it's transversal for y, and it's a contact for x. Here's a contact in both sides. This contact could be cubic 2 or of order, even order, for instance. Okay. And the type of contact that we are going to use in our work are the visible fold regular contacts, which are given by a visible fold. It's called visible because we can see the trajectory which is touching the discontinuous surface. For instance, we have a contact here, but you can't see the trajectory touching the surface. In this case, we call it visible because we see the trajectory. And this is followed by one side, and we assume that's transversal by the other side. This situation can happen also in higher dimensions. For instance, if we have a three-dimensional vector field, in a point of fold contact, you actually have a whole segment of fold contact. So here, the trajectory behaves like this. You have a surface touching the switching, the discontinuous surface. And for the vector field below the discontinuous surface, we will assume that it's regular, it's transversal to the discontinuous surface. Okay, so it is the Filipov. The Filipov system consists of things like that. Okay. Now let me introduce the definition of sliding Shilnikov orbit. We start with a three-dimensional vector field. This three-dimensional vector field has a region of sliding. Okay, so all the vector fields, all the trajectories are reaching this region from above and from below. Okay, and this line is the boundary of the sliding vector field. The boundary of the sliding region is always a set of contacts. Okay, so we assume that we have a pseudo equilibrium, which is an unstable focus for the sliding vector field. Since P is in a sliding region, we already have an unstable direction. Then the other direction must be unstable in order to get a Shilnikov connection, or something like a Shilnikov connection. We also assume that we have a fold regular point here. The vector field below the surface is transversal to the surface at this point. And we assume that the backward trajectory through the sliding vector field of these points approach to the pseudo singularity asymptotically. And finally, we assume that the forward flow of Q by following the vector field X, which is defined here, reads P now in a finite time. Okay, so this is basically the structure of what we call it by sliding Shilnikov orbit. Okay, so at this point, one may ask how easy is to find example of Filipov systems having sliding Shilnikov orbits. So to answer this question, we come up with a piecewise linear example. Okay, so Z is piecewise linear, it's constant. Okay, it's a fine system. It's has constant in the first entry and linear in the other one. And we proved that for this system, whenever alpha and beta are positive, the origin is always a hyperbolic pseudo set of focus of Z, which is an unstable hyperbolic focus of the sliding vector field Z tilde. Moreover, Z has a sliding Shilnikov orbit connecting P, which is the origin, to itself passing through the visible fold regular point. So we prove that for any alpha and beta positive, this system, this piecewise linear system, has a sliding Shilnikov connection. To see that, I show a simulation which was done in Mathematica for some specific values of alpha and beta. So Q here is a fold regular point, the visible fold regular point, and the trajectory passing start at this point converges in the past to the asymptotically to the focus of the sliding vector field, and the forward trajectory reaches the pseudo equilibrium in a finite time. So this is how a sliding Shilnikov orbit looks like in these piecewise linear examples. Okay. So since the sliding Shilnikov orbit is a global connection, is a global object, it's always interesting to understand how to break this connection. So this is what is stated in the theorem. If we have a vector field Z0, which has a sliding Shilnikov orbit, then we can find a small neighborhood in the space omega r, in the space of piecewise smooth vector fields of Z0, and a codimension 1 manifold inside this neighborhood, satisfying that a vector field inside the Filipov system inside W has a sliding Shilnikov connection if and only if it lives in this codimension 1 submanifold. This means that in order to break the connection, that means in order to leave this codimension 1 manifold, I need just one parameter. So we can define a curve in the space of Filipov systems, a curve inside W that Z mu that cross this codimension 1 surface passing through Z0. Okay, and we could assume that this intersection is transversal. So in this case, this situation, Z mu is called a splitting of gamma 0. Okay, so this basically is stating that this connection is also a codimension 1 phenomenon. Okay, now in order to produce versions of Shilnikov results, we need to understand what would be a periodic orbit close to a sliding Shilnikov connection, sliding Shilnikov orbit. So that's what I'm going to illustrate here. So consider a point which is sufficiently close to Q, which is the fold regular contact where the Shilnikov connection is passing through. Since the intersection of the forward flow of Q with the sliding region is transversal, because it is a sliding region, then for Q1 sufficiently close to Q, the forward trajectory of Q1 also intersects the sliding region, also reach the sliding region in a finite time. Then by Q1, we would have a periodic orbit if after touching the sliding region, the trajectory is sliding back to the initial condition, Q1. This is a second example. Q2, it reaches the sliding region, and then it slides back to Q2. So these are the picture. This is the picture that we have to have in mind when I'm talking about sliding one periodic orbit. Okay, and the one here is because of when we look at the Poincaré map, this corresponds to fixed points. Okay. So regarding this kind of periodic orbits, we have the following result. If Z0 is a Filipov system which has a sliding Shilnikov orbit, then for if we take any neighborhood of gamma 0, we can find inside this neighborhood infinitely many periodic orbits of this type. Okay, so here it's not necessary any additional hypothesis like Shilnikov conditions. Okay? If you have a slide Shilnikov orbit, you have infinitely many periodic orbits close to this Shilnikov orbit. Okay, and if you break the Shilnikov orbits, the new system, the Z mu, will have infinitely many periodic orbits of period 1. However, this amount of periodic orbits is increasing to the infinity as mu goes to 0. Okay. Here, when you break the sliding Shilnikov orbit, you have assured the existence of a finite number of sliding one periodic orbit. Okay, but we will see that we still have infinitely many periodic orbits if you consider higher periods. Okay, so to prove this theorem, what we have to do is to study and define the first return map and see what's happening. So we start a Shilnikov connection, and we take a small neighborhood of this fold regular point in the line of tangents. Okay, since it's a fold regular point, we can take this neighborhood sufficiently small in order that every point in this neighborhood are also visible fold regular points. Okay, since the backward trajectory through the sliding vector field of these points converge asymptotically to P, we can take gamma r sufficiently small in order that all this neighborhood also converges asymptotically to P. Okay, and since the forward trajectory of Q through the vector field of X reaches the sliding region transversally, we can take again R sufficiently small, if necessary, smaller if necessary, in order that the forward flow of each point or of all this neighborhood reaches the sliding region transversally. It will reach the sliding region in a curve that we call mu r. So as we can see here, this curve intersects the saturation that we call it by SR infinitely many times. Okay, so for each intersection we give a name of E1, E2, and so on. Okay, so the properties we have here is that all these segments are disjoint from each other, and they converge to P as Y increase. Okay, so for each one of these segments, we consider the inverse image by the diffeomorphism defined between gamma R and mu R. Since this intersection is transversal, of course, we can define a diffeomorphism between these two curves. And for each one, we consider the inverse image and we define the segments J's. Okay, so for each I, we have a Ji defined here. And for each one of these J's, we have well-defined the first return map. So if we take UR as the union of all J's, we have a first return map defined in a non-connected set. Okay. So for each one of these segments, we can apply the Brouwer fixed point theorem and obtain automatically the existence of a fixed point map, a fixed point for the first return map. So for each one of these segments, which are infinitely many converging to the point P, we have a periodic orbit. So we have concluded the existence of countably infinitely many periodic orbits. Okay, so in 2017, with Pons and Varão, we were able to prove, we studied with more attention the first return map defined in a neighborhood of sliding Shilnikov orbits. We were able to prove that there exists are positive sufficiently small. That means we can take the neighborhood of Q sufficiently small in order that the derivative, the modulus of the derivative of the first return map is always greater than 1. So what does it mean? Let me draw the first return map here. Okay, so let us consider the set J2. If we come back, we see that the extrema of J2, the closest extrema of J2 to Q, it goes to the extrema, which is the closest one to P, and then if we follow the flow, we see that the image of this point is minus R. Okay, and analogously, the image of the other extreme of J2 is R. It goes to here. Okay, so when we draw this first return map, we see something like that. In this situation, it starts in R, decreases to minus R, and cannot change the inclination because the derivative is never 0. Okay, so we have a very similar situation to the smooth context where we have oscillate, where the graph of the one-dimensional map oscillates to the origin and intersect when the Shilnikov condition holds, intersected the identity infinitely many times. Here we do not have an actually continuous oscillation because the domain of our first return map is not connected, but we have these sort of defined regions where the inclination, the function is always decreasing. So you also have this type of oscillating phenomena here. And for the other side, you have increasing branch. So all this sets accumulates to the origin, and what we have here when you see to the identity is that it crosses the graph of the first Poisson map infinitely many times. Okay, so studying this first return map with more attention and with more details, we were able to conclude that for each natural K, we can find an invariant an invariant set for the first return map and a p-invariant contour set, lambda k, such that the first return map restricted to this invariant set is conjugated to a Bernoulli's shift, okay, in this symbolic space. This is a symbolic space with finite symbols. So sigma 2 is the usual one, the sigma k star is this, which is the same. The only difference is that we are starting counting the symbols by one. The usual notation starts from 0, okay? It's not a significant difference. So all the properties we have for Bernoulli shifts, we can translate in our situation. So in our context. So the first return map is transitive. It has sensitive dependence on initial condition, and also have dense periodic orbits, etc., etc. And we can improve a little more this result. And if we take lambda as being the union of all these lambda k, we can actually find a conjugation between pi restricted to lambda and Bernoulli shifted in a symbolic space with an infinite number of symbols. Okay. So this basically describes completely the dynamics of the Island Shilnikov orbit. Okay, so now let me talk about a little about the application of this concept and the results. In 2016, I was invited to be attending to this intensive research program in CRM, which for me was a memorable event. And I had the pleasure to be attending to a talk given by Sophia about this very nice paper. Here, in this paper, they studied the interactions between some species using real data. Okay, they studied the interaction between some species of some phytoplanktons and ciliates in the Lake Constance. Lake Constance, which is a freshwater lake in Germany. Okay, and they developed a Filipov model to understand the interaction between a predator and two preys. The predator was the ciliate and the preys are different species of phytoplanktons. And the idea here is that the idea of the model is that the predator tends to feed most heavily upon the most abundant prey species. Okay, so we have two preys, one predator, and the predator tended to feed, tended to switch the food preference according to the availability of the preys in the environment. So this is the model. Okay. This function H basically measures the availability of the preys, okay, depending on some parameters. I'm not going to details of the parameters, but it's measuring basically what's the most available prey. And when H is positive, P1 and P2 are the preys, or the density of the preys, and capital P is the density of the predator. So when H of P1 and P2 is positive, there exists an interaction between the predator P and the prey P1, while the prey P2 grows exponentially, of course, if R2 is positive. So the prey eats on prey 1. Okay. Eventually, the population of prey 2 increases and the population of prey 1 decreases, and this function changes its signs. Okay. So in this situation, we see both systems are Lotka-Volterra systems. Okay. So in this situation, we can see that now the prey1 increases exponentially if R1 is positive. And now there exists actually an interaction between the predator P and the prey P2. In this situation, the predator eats only the prey P2. And the same happens, the same thing happens. The species prey1 increases, now the species prey P2 decreases, and again, this function changes its sign. And there is a switch in the behavior of the predator, and of course in the model then we use switch between the both systems. Of course, this is an idealized model, and it's assumed that the switch between the food preference of the predator happens instantaneously. Okay, it's a sudden change of behavior, and of course this is what induces the discontinuity in the model. It's quite difficult to study this model because it has a lot of parameters. Actually, it is the space of parameters is contained in a Euclidean space of dimension 9, and it's not that there are some restriction among the parameters, so you cannot consider all the whole space R9 to study your problem. So you have actually to work in this parameter space and respect all those constraints. Okay. So in the Sophia's talk, she showed some graphs which suggest a possible cascade to chaos, and those are the graphs. Okay, basically they discovered that in the system, that this system admits sliding periodic orbits at the same time that I have showed previously. Okay, so or those are sliding periodic orbits. It leaves the period, the discontinuous surface through a fold regular contact. Then it returns to the slide region and slides to the initial condition. And they were able to numerically detect that these periodic orbits starts to bifurcate in more periodic orbits. So it's a kind of period doubling bifurcation. We start with a single periodic orbit, then it splits in two periodic orbits, and so on. And eventually, in a critical value of the parameter, you have infinitely many periodic orbits, which is something very similar that is happening in our situation when we are working with slide Shilnikov orbits. And then, when she showed these figures, I realized that eventually I could try to use the theory that we have developed for sliding Shilnikov orbits in order to try to actually prove that for some choice of the parameters of the system, the system actually behaves, actually presents a chaotic dynamics. Okay, so that is what we have done in this work, 2020. We were able to prove, we were able to find a codimension 1 submanifold any of the parameter space, such that the model possesses a sliding Shilnikov orbit whenever the parameter is in this codimension 1 manifold of n. Okay. Moreover, we were able to prove that actually there exists an open set in the parameter space containing the codimension 1 submanifold, such that the models behave chaotically whenever the parameters is in this open set. So this is basically a simulation of what is happening in the system. Here we can see the slide Shilnikov connection, and these are the projections of those orbits. Here there are two trajectories. Here are the projections of the trajectories which starts very close to each other, and the usual thing happen. No, it starts very close, and suddenly you cannot distinguish the orbits any longer. Okay. So in order to find this example, we fixed some parameters, and the example for the numerical example, okay, this is not what we have done to prove analytically the existence of the Shilnikov connection. But for the example, for the numerical, to draw the pictures, we fix all these parameters. These parameters fix a very nice structure here, a very useful structure here, which are the sliding, the fold line. Here's the fold line, in black is the fold line. And the fold line we have, when we follow one of the trajectories of the continuous system, we have this red curve, which is the return line of the fold line. So the fold line returns, follows the trajectory of the vector fields, and returns to the sliding region. This structure is the same in the three situations, okay? And we let one of the parameters, the beta 1, to be free in order to change what's happening here. But this structure is fixed, and what changed with beta 1 is the position of the focus in the sliding vector field. So for beta 1 equals 6, the pseudo equilibrium is below the return curve, red, and for beta 1 equal 10, the pseudo equilibrium is above to the red curve. So eventually, this pseudo equilibrium has to be in the return curve, and then we have assured the existence of a Shilnikov connection. So those are the reference. The first one is where we studied the Filipov type predator-prey model. The second one, we have studied the first return map and provide a completely ergodic description of the first return map defined near a Shilnikov orbit. Here is where I published the part of my thesis regarding introducing this object, and this is the paper of Sophia and co-authors where they introduced the model that we have studied. So thank you very much for your attention.
So thank you very much, Professor Novaes. So let's thank Professor Novaes for his wonderful talk. So, are there any questions or comments? If someone has a question, please just unmute himself and go ahead, please. Questions? So, there are no comments? No. So if there are no questions, let's thank Professor Novaes again. Thank you very much.